Go ahead.
Okay, thank you. Oh, sorry, wait a minute.
Ruquan, it seems we cannot hear the voice. When you share the screen, please make sure you check the box of share the sound of your PC.
Okay.
When you click the share screen, on the left corner, there is a box to check. You have to first click share screen, and then on the left corner, you will see a checkbox.
Checkbox.
Actually, you can let Professor Zhang to control your computer, so Professor Zhang can.
Sure. Yeah.
Okay, you can. Yeah, I'm not familiar with Zoom.
Could you first share your? Yeah, let me see how to do that. If I can remote your, how do I remote?
I can see.
Could you share your screen again?
Okay. Just wait a minute. I hope I found the. Everyone, my name is. Can you hear me now?
Yes. Yes.
Okay. Thank you, sir.
Ruquan from China University of Petroleum. Hello, everyone. My name is Ruquan from China University of Petroleum, Beijing, and the University. Our topic is CO2 utilization and sequestration in reservoir, effects and mechanisms of CO2 electrochemical reduction. The research will be introduced in the following 4 parts. First of all is the motivation. With the inevitable aggravation of the greenhouse effect, CO2 emission reduction has become the human consensus. Herein, CO2 sequestration technology was given greater expectations, which can be separated into the physical method and the chemical method. CO2 and the AOR technology as a representative of the physical sequestration method was regarded as the most promising CCUS technology for its large sequestration amount and excellent economic feasibility. However, increasing found several serious technology. First of all, the CO2 channeling in the ejection and the CO2 leakage in the sequestration was usually serious due to the inherent heterogeneity of the reservoir. The injected CO2 are preferentially flowed through the hypermeability parts and finally produced from the production well. That is, formed the insufficient circulation, which results in the low oil recovery and the low CO2 sequestration efficiency. Moreover, the gaseous CO2 accumulation can cause the secondary geological disasters. CO2 electrochemical reduction as a representative of the chemical method is how we increasingly concerned in recent years for its high CO2 sequestration efficiency and the permanent sequestration characters. However, the small sequestration amount and the low economic feasibility largely hindered its applications and promotion. Regarding this, we try to introduce the CO2 electrochemical reduction into the CO2 EOR, CO2 and EOR technology, we make full use of the advantages of both technologies. Experiments were conducted to investigate its effects and mechanisms. The second is a method. First of all, we synthesized the catalyst. Then the efficiency of the synthesized catalyst was evaluated using the electrochemical experiments. Subsequently, the efficient proved synthesized catalyst was used in the co-flouring experiments to investigate the effects of this technology on oil recovery and the CO2 efficiency, sequestration efficiency. Finally, the contact angle and the interfacial tension experiments were implemented to unravel the mechanism of this technology. The facial hydrothermal method was used to synthesize the tin dioxide catalyst. This is the apparatus for electrochemical experiments. The H-type electrolysis cell was used, and the anode is platinum actual, and the cathode is the tin dioxide coated glassy carbon electrode. This is the apparatus for co-flouring experiments. The co-holder was customer designed and built. The anode was placed in the production side, and the cathode was placed in the injection side. This is the apparatus for contact angle and interfacial tension. In this apparatus, the high pressure and the high temperature can achieve. The third part is the results and discussion. As displayed by the scanning electron microscopic image, we can see that the synthesized tin dioxide catalyst has a clear three-dimensional hierarchical and porous structure, in which the secondary structure is a lamellar tin oxide crystals of 40 to 100 nanometers. This special microstructure increases the surface areas, the numbers of active sites, and the CO2 electrical reduction efficiency. The XPS results, XRD results, and the EDS results collectively proved the synthesized tin dioxide catalyst is high pure. Two benches of electrochemical experiments were conducted. One in the CO2 condition, the other in the nitrogen. The difference of the current density can be attributed to the CO2 electrochemical reduction. This is the Faradic efficiency, and this is Fermi's protection rate. Clearly, the synthesized tin dioxide catalyst activates CO2 electrochemical reduction and converts CO2 into formate, which rated strongest at 3.75 voltage. The stable current, the stable current density and the Faradic efficiency within the 24 hours illustrates that the high durability of the tin dioxide catalyst for CO2 electrochemical reduction. this is the performance comparison of the synthesized tin dioxide catalyst with others. No matter the Faradic efficiency and the current density, the synthesized catalyst is in the middle place. Considering the multiple factors including the synthetic complexity and the catalyst stability and economic feasibility, the synthesized tin dioxide catalyst is relatively better and can totally fulfill the demands of the following co-fluoriding experiments. These are the co-fluoriding experiment results. These are the oil recovery. This is the performance of the water fluoriding. The pink star is ordinary CO2 and AOR technology. The red circle is this technology. The right is the CO2 sequestration efficiency. This is the injected CO2. These are the produced CO2, and the difference is the sequestrated CO2. Obviously, this technology notably enhances CO2 sequestration efficiency and oil recovery, and the cell potential increases CO2 sequestration efficiency and the CO2 and the oil recovery increase to the maximum at the 3.75 voltage and then decrease. Current density and the Faradic efficiency and the format production rate validates the occurrence of the CO2 electron reduction into the co-fluoriding experiments. This is the results of the contact angle and interfacial tension. These are the crude oil contact angle. This is the interfacial tension of crude oil. These are the CO2 contact angle. It's obvious that this technology has a significant impact on the CO2, crude oil, brine, and rock interaction. This technology reduces the contact angle and the interfacial tension of crude oil. Moreover, this technology enhances CO2 wettability of the rock surface. Both of them reach the strongest at 3.75 voltage. Discussion. This is the discussion. The right is CO2 electron reduction into the electrolysis cell. These are in the reservoir. The porous media, the flowing fluid, and the high pressure of the reservoir provides the reaction space, accelerates the charge transportation, and enhance CO2 dissolution respectively, which supplies the excellent conditions to CO2 electrochemical reduction. CO2 is electrically reduced into formate, enabling massive and stable CO2 sequestration. Formate acts as a surfactant to enhance oil recovery. Additionally, produce crude oil provides a larger pore volume for CO2 sequestration. CO2 electrochemical reduction enhances CO2 wettability of the core samples, increase the CO2 trapping and retention in reservoirs, also enhances the CO2 sequestration. The last part is the conclusions. A novel, efficient, and economically viable CO2 utilization and sequestration technology was proposed. This technology enhances the oil recovery and the CO2 sequestration into reservoirs. This technology converts the injected CO2 into the format to sequestrate itself, and meanwhile, alters the crude oil or CO2 brine rock interactions, resulting in the enhanced CO2 wettability and consequently increases CO2 trapping and retention, causing the weakened oil wettability and then enhance the oil brine interactions and finally enhance the oil recovery. This technology is a promising CCUS method, more deeply studies required in the future to investigate its in-depth effects and mechanisms. Yes, that's all. Thank you. Any questions? Thank you.
Thank you, Juan, for sharing the screen and play the video for us. Now it's the Q&A session. Anyone, please feel free to ask the questions.
So if nobody have a question, can I ask one?
Sure, please go ahead, Professor.
Yeah. Okay, so I didn't quite get it. So the contact angle in the CO2 liquid system is like a kind of CO2 weight. That's what you got?
Yeah, it's a CO2. It's a CO2 bubble on the rock surface in the solution.
The contact angle through the CO2 phase is less than 90 degrees C, 90 degree, right?
Yeah.
Okay, so it's like a gas weight, right?
Yeah.
Okay, that's very interesting. Yeah, because actually, I have done some research in the gas weight system. I don't know if you have noticed that. Yeah, so you can maybe check out some our publications. Yeah.
Yeah, sir. Yeah, you know, in this experiment, the electricity, the direct current was applied on the core samples. So there are so many maybe different phenomena. Yeah, it's very confusing.
Can you do me a favor? If you have slides, for example, you show the contact angle before and after the electrochemical reactions, because usually the CO2 liquid system is liquid weight, right? So that means the contact angle through the liquid phase is less than 90 degree, right? So you showed it's opposite, right? After the electrochemical reactions, right? So do you have the comparison of these two pictures?
No, we are now conducting some experiments at your side, but we haven't get the final conclusion. Yeah, we will continue to this part. Thank you, sir.
Okay, yeah, because this is very interesting, and I just like to know the comparison. Yeah. Okay. Thank you.
Thank you, sir. Thank you.
Okay, thank you very much for the questions from Professor Lee. Now I see the Professor Brian to raise your hands. Please unmute yourself and go ahead to ask questions.
Yes, thank you. Ruquan, this is an interesting idea. Could you tell us what is the concentration of formate in the fluid that you're injecting? So the limit would be pure formic acid. I'm guessing that you're somewhere between, maybe it's dilute formic acid. Could you tell us the concentration of formate in going into your core?
Oh, sorry, sir. Professor, I can't. Can you repeat the question?
Yes. So you're converting CO2 to formate.
Yeah.
And then you're injecting that into the core. What's the concentration of formate in the fluid that you inject into the core?
Concentration it's 0.5 sodium, sorry, it's molar is 0.5 molar sodium hydrocarbon. Yeah, injected into the reservoir, into the core.
So formate is very soluble. You presumably could make it more concentrated. Is that true?
Yeah, more. Sorry, sir. This question we haven't started this part.
Okay, thank you.
Yes, sorry.
Okay.